Alright, this is the smaller review that I handed out in class. Not the large extra credit review, the smaller one. And basically, if you remember, we said that there was actually only about 5 major topics on the thermochemistry exam. And I figured, why not just pull an example of each type or each class of problem and go over it. Now in class, we kept track of answers on the board. All right, and a lot of us check our work that way, but we did not have time to actually go over each individual question, so I'm going to take the opportunity to do that right now. All right, the first one. 5,196 joules of energy are required to raise the temperature of H2O from 24.5 degrees Celsius to 75.4 degrees Celsius. How many grams are in the sample? Okay, first off, it's up to you to figure out that we're talking about one substance. This isn't a time where we're heating up a bolt or a ring or some metal object and then throwing it in water. No, we're basically just warming up our water, maybe in the stove or something like that. We're just going to warm the water up. All right, so it's just one object, and that's just a Q equals MC delta T. Now I give that to you right here, but it would be up to you to figure that out, on your own. This is just a warming problem. Q equals MC delta T. Okay, whenever we're doing these problems, okay, it pays to be diligent and to make a data chart. Q, M, C, delta T. All right, make a data chart. We're looking for mass. What are the grams that we're looking for mass? We're given Q, 5,196 joules. Now you should ask yourself, is that going to be positive or negative? It's raising the temperature. It's a positive value, okay, endothermic. C is not given in the problem, but it's water, and we know water specific heat. 4.184 joules. I'm going to say gram degrees Celsius. Change in temperature. Basically, we just have to subtract those two. All right. So I have 75.4 is the final minus initial. 24.5. I get 50.9. All right, that's degree C. Basically, it's just a plug and check. If it were me, I would solve for the variable first. Mass equals, okay, hopefully you can follow this, Q over C delta T. Of course, you could do it the other way by putting values in and then isolating the M. All right, that's perfectly legitimate. Plugging my values in, I get 5,196 joules. That's a J over 4.184. Joules, gram, degrees Celsius, parenthesis, 50.9 degrees Celsius. Okay, a little close to the edge. Well, joules are going to cancel with joules. Degrees Celsius will cancel with degrees Celsius. We're left with this guy in the denominator. It's a gram. It's a G. All right. Denominator and a denominator, you take their reciprocal. Our answer will be in grams, and that's what we're looking for is mass. Okay, let the units dictate the direction the problem's going. All right, you're going to run this through your calculator. 5,196 divided by 4.184 divided by 50.9, and you're going to get, I believe, 24.3. 24.4. All right, so the answer is 24.4. All right, so I'm going to erase everything and just say the answer, hopefully you did this one at home or in school, 24.4 degrees Celsius. Those are typically some of the easier questions because it was just one set of data to deal with. All right, onward. A 35-gram sample of unknown metal was heated to 198 degrees Celsius and put into 232 grams of water at 34 degrees Celsius, raising its temperature to 39 degrees Celsius. What is the specific heat of the metal? Oh my. A lot of stuff going on. A lot of stuff going on. And this is actually a thermal energy transfer. I'm going to heat the metal up, via a torch, a stove, whatever, an oven, and I'm going to transfer it over to the water. So this time we're going to have two sets of data. All right, because our new equation is not going to be Q equals MC delta T. It's going to be MC delta T equals negative MC delta T. Okay, one side must be negative in order to keep it equal. All right, because one object is losing energy, okay, that would be the metal. It's hot, it's going to cool down. The metal is losing energy, the water is gaining. All right, one side must be negative. Typically, you would put that to the losing side. That would be the metal. Doesn't really matter, though. So the first thing you have to know is that these M's and C's are not the same. Okay, so we need a table for that. And I apologize, this marker is giving me some issues. All right, so I'm going to give H2O values first. Q, M, C, out of order, delta T. All right, when you do that, you're going to see that the water goes from 34 to 39. Okay, water's temperature goes up 5 degrees. How heavy was my water? I'm doing the water side first. It was 232. The C value, and I realize now I'm running out of room. I do not need Q. We're getting rid of Q because we're setting them equal to each other. So let me just amend this just very slightly. Okay. So I have my delta T, I have my M. The C for water, you should know, is 4.184. We've used that now probably 30 times. Grams per degree Celsius. Next comes the metal. The C, the M, the delta T. First of all, we're looking for the specific heat. We don't know that. We know the mass of the metal, though. It's 35 grams. We know the delta T. Okay, this one gets a little tricky. It's going to be 39, final minus initial. 39 minus 198, negative 159. All right, negative 159 degrees Celsius. Okay, we have 6 variables. We know 5 of them. We can stick those values into the equation and solve for C of the metal. All right, I'm going to pick that C. Most people, I'm not going to solve this one because, to be completely honest with you, most students, when they have issues setting the chart up. Typically, the main issue is this guy right here, 39 degrees Celsius. Okay, why is that so difficult? Well, you have to realize and you have to know that in all these examples, when you have 2 objects coming into contact, final temperature is the same for both. Okay, same for both. Okay, always, whenever you're dealing with this equation, TF is the same. Okay, TF is the same. So I used the 39 degrees Celsius for both sides to get my 5 and my negative, my negative 159. All right, and that's pivotal. You just have to slow it down and read these very carefully. I'm not going to do the algebra on this. I'm running out of room. All right, and I apologize for that. But if you do the math on that, you're going to find out that the answer is, where am I at? The answer is C equals 0.872 joules over gram degrees Celsius. All right, and if you don't believe me, and I implore you to do this, especially if you have time, plug it back in. All right, if I put this C value here, I should be able to multiply these 3 components together, and I multiply these 3 components together, and they should be the same but opposite. Okay, this would be negative because the negative 159. This would be a positive value. Okay, they're going to be the same but opposites. That's why we need the negative there. All right, onward. That's 2. What do we have here? Thermostoic. Okay, it's not even really stoichiometry because we're not using the mole-to-mole ratio. I'm going to get a little extra elbow room so I don't have that problem again. And let's have it. Okay, I have a reaction here of an acid-base. I guess sulfuric acid and sodium hydroxide combining to make water and sodium sulfate. I have the enthalpy of reaction, should be a capital J. Okay, 34 kilojoules. All right, negative 84 kilojoules. Negative 84 kilojoules. Okay, negative 84 kilojoules, that is when one reaction occurs. And what I mean by that, that is a reaction, negative 84 kilojoules of energy is the change when 1 mole of H2SO4 and 2 moles of NaOH and 2 moles of water and 1 mole of sodium sulfate interact, okay? The reactants making the products, obviously. Okay, so that negative 84 is important. It goes along with the coefficients. What is the thermal energy change when 34 grams of NaOH react with 54 grams of H2SO4? It's a limiting reactant problem. We have both reactant numbers. Okay, we have masses for both. Okay, well, what do I have here? I have my 34 grams of NaOH, and I have 54 grams of H2SO4. Grams in our class, the only time we ever used grams was in this chapter. Okay, it had to do with Q equals MC delta T. That's the only time we actually ever use mass. We always use moles instead. Moles are the interchange for chemistry. And when you look up your Na, which is 23, and your oxygen 16, and your H is a 1, you're going to get 40 grams of NaOH and 1 mole of NaOH. Okay, we're in moles. Now what? Okay, this is not regular stoichiometry. The next step in regular stoichiometry would be the mole-to-mole ratio. Instead, we're going to use our thermostoic method, which is delta H over the coefficient. Delta H over the coefficient. And that's always how it works. There are 2 moles of NaOH. And when 2 moles react, there are 2 moles react when 84 kilojoules are released. Okay, negative means it's released. Or you could think of, it's the same but opposite, you could think of 84 kilojoules of energy are released when 2 moles react. Okay, either way. You're going to cross this out. Our last unit standing is now kilojoules. Run the numbers through. You're going to get a negative 35.7 kJ. All right, I had a huge tech glitch, so you may see that we switched colors and all of the work for the preceding half a problem disappeared. We were at finding negative 35.7 kJ from the 34 grams of NaOH. All right. Something like that. Those are steps. Well, this is a limiting reactant problem. We have both reactant values, okay, which means we have to take both reactant values into account. We also have H2SO4. All right, just like before, grams do nothing for us unless it's a Q equals MC delta T. Moles are our friends. Let's get over to moles. 1 mole of H2SO4, 4 oxygens is 64, plus another 32 makes us 96, plus nu is 98 grams. All right, and I'm impressed that a lot of us actually have quite a few of those masses memorized. It makes life so much easier. All right, now I'm in moles. And just like before, it's going to be the delta H over the coefficient. It's, again, negative 84 kilojoules, just like before. This time it's not over 2, but it's going to be over this coefficient 1. All right, so it's over 1 mole of H2SO4. Moles H2SO4 cancel out. All right, when you do the math for this, it's going to be a negative 46.3. Now, in our stoichiometry chapter, we picked the lower value. Okay, limiting reactant would be the one that, the reactant that produces less product. Still the case, except we don't say lower, we say closer to 0. All right? Basically what I'm saying is the 34 grams of NaOH releases less energy, okay, than what our H2SO4 has the capacity to produce. So this is the value of what the thermal energy change is, a negative 35.7 kilojoules. All right, a lot of us think this is much easier than the stoichiometry we're used to doing in the other chapter. If you remember the other chapter, we could have problems that went maybe 4, 5, 6 steps long. Typically, we're only seeing these 2-step problems over and over and over again. There's no need to do the mole-to-mole ratio. There's no need to switch chemicals. All right, onward. One of our standalone concepts. Get some more room. I'm looking for delta H reaction from the heats of formation. Okay, I'm asked to find the delta H for CB in this case. And I have some heats of formation for 3 of the 4 components, but not the last one, the CB. I have the actual reaction value. All right, what we're looking for here is the products minus reactants. I call this a standalone concept because you could just come in and do this after 20 minutes, a 20-minute talk. It's not reliant on as much of the 4, 5, 6 months, like a lot of our concepts are. It's kind of like a little vacation, which is nice to have every once in a while. Okay, we want the formations of the products minus the reactants. Products minus reactants. Okay. Well, I know that the delta H reaction is negative 84. Again with the little j. And I want to do in summation, and I probably should put this both in parentheses because that's how we do them. I want to know, put the product information, and then the reactant information. Products minus reactants. And you're going to find that, again, 1 mole, coefficients are important, 1 mole of A3D2 releases 81 kilojoules of energy, plus 6 mole of, I'm going to call it Y. Variable Y. Realize it's a little difficult. Again, this tablet is not cooperating today. That's going to encompass my product values. Products minus reactants. Okay, reactants would be 3 moles of AB2, negative 43 kilojoules per mole. Moles cancel out. Plus my my C3D, I have 2 moles, negative 23 kilojoules. I apologize for writing so small. Again, the technology is not being very friendly. All right, I know that's sloppy, so let's just go over it really, really quick. 1 mole, that's from here. 1 mole of my A3D2. 6 moles of the CB, unknown value for that one. 3 moles for the AB2 times its value, plus 2 moles times the negative 23. That's this value. Again, the coefficients times the value. Add them up. Okay. And when you do that, I'm going to get my 6 mole Y, okay, minus 81 kJ plus 175 kJ. Looks just like that. Okay, when you settle it out, clean it up a bit. And I realize it's a little bit on the sloppy side, and I apologize for that, but we all have enough math to figure that out, okay, to actually read through that. You can see that there's a minus issue. You have to get used to it. Subtraction, negative numbers. You have to just figure it out from there. Okay. In order to find out what my 6 mole, or what my Y is, I have to add 81 to both sides and subtract 175 from both sides. When you do that, you're going to get a negative 178 kilojoule equaling 6 mole Y. Divide both sides by 6 moles and you're going to get Y equals a negative 29.7 kilojoules per mole. Okay, if this was an exam, and that's what we're looking for, if this was an exam, what I would then be doing, especially if I had more time, that's our answer. Maybe it's right, maybe it's wrong. I can find out. If there's extra time, I'm going to take this value right here, and I'm going to plug it into there. And I'll run all these numbers through my calculator and see if they come out to be negative 84. Okay, it's a great check mechanism that's built in. All right, you have to take advantage of those when you get them. I know a lot of us have a tendency to ignore those types of things, but it really can help save you some points. Okay, lastly, Hess's law. Let me get us some extra room. Hess's law is our second standalone concept. All right, a lot of us had a little bit of issues at first, but I think we worked them out. Hess's law, the whole concept is a matching game. I have to orientate or manipulate my 3 reactions that are given in order to match the overall. Okay, the whole goal is to find the delta H of this reaction. It's not on there, but let's just put it in there. Okay, I want to find that delta H of the overall. And how do you do this? Well, you look for uniqueness. Okay, you look for things that are unique to each reaction. What I mean by that is, what piece of the given reactions only matches the overall. Okay, it's not redundant, it's not in multiple steps, it only matches the overall. What I mean by that is, when you look at this first reaction, it has carbon. Carbon's not unique, it's down here. It has oxygen. Oxygen's not unique, it's down here. Yield CO2. CO2 is not in the other steps, but it shows up here. That is the unique aspect. We need 1 CO2 in the product side. Turns out we have 1 CO2, it's already in the product side. First reaction is good to go. What's unique about the second step? Sulfur is not unique, it's there. Oxygen, we already said, was not unique. SO2. Looking up here, we need not 1, but 2 SO2s, and in the product side. Well, ours is not, it's in the product side, that's good, it's not 2. So I have to multiply the whole reaction by 2, and then also the delta H by 2. Okay, I'm just going to go ahead and rewrite that right now. I have 2 S solids plus 2 O2s, now yielding 2 SO2s. And my new delta H is equal to a negative, I'm actually going to have to crunch this really quick for you. I should be able to do this in my head. 296.8 times 2, a negative 593.6. Okay, negative 593.6 kilojoules. We're done with this reaction now. We're done with it. I'm going to just get rid of it. We replaced it. We manipulated it and replaced it with our new reaction that matches perfectly to the overall, which is what our goal is. Okay. Onward to the third reaction. Third reaction has carbon. It's redundant. It's in the first. It has sulfur. Sulfur's already in the second. That's no good. CS2. CS2 we need. Okay, we need one CS2. We got one CS2. We're perfect. Oh. Unfortunately, our CS2 is a product. We need it to be in the reactant side, so we have to flip it. Okay, when I flip it, I'm going to take the minus, or the opposite, of the delta H. Okay, so it's now going to be a negative 87.9 kilojoules. And when I do that, I'm going to have CS2 liters. I should really skip the state symbols. Carbon plus 2 sulfurs. We have our 3 steps now. We manipulated all 3. We didn't have to do anything to the first one. All right, I'm going to switch to blue. We have this step. We have this step and this step. All 3 of these should add up to be our overall. Now I'm going to do an error check analysis and actually look and see if it works out. All right, carbons cancel with carbons. Carbon's gone, carbon's gone. Oxygens don't cancel, they're going to gain up. Sulfurs, I have 2 sulfurs here, they're going to cancel 2 sulfurs here. Okay, CO2 doesn't cancel, SO2 doesn't cancel. Okay, what do I have left? I have O2 plus 2 O2 plus CS2 yields CO2 plus SO2. I'm sorry, QSO2. And that's exactly what we're looking for. We got it. The answer to this problem of what the actual delta H is going to be is quite simply going to be add up all these values. Okay, the answer is going to be a negative 393.5 kilojoules plus a negative 593.6 kilojoules plus a negative 87.9 kilojoules. All right. So the delta H is going to be our 3 steps that will now make our overall. The delta H, the overall, is the combination of our 3 steps. And when you do the math to that, okay, I have to gain some room, you're going to get a final answer of delta H being equal to a negative 1,075 kilojoules. Hess's law is not overly difficult. It is time consuming. All right, it is time consuming. You just have to slow it down a little bit, and match up what you're given to make it look like the overall. Okay, what are you allowed to do? You're allowed to flip it. When you flip, you take a negative of your delta H value. You're allowed to multiply by any value you see fit. You're also able to divide by any value you see fit. All right. Hopefully, with these 5 examples, you're going to be in much better shape for the exam come next class. And I hope to see very good results.